So I'm going to present my second lecture in the series of Digital Signal Processing Made Easy. In this, I will explain how to represent the basic discrete signals, some standard discrete signals, and some basic operations performed on the discrete signals. So in lecture 2, I will start with the discrete time sequence, how to represent it. As we know, discrete time signal or sequence is nothing but a sequence of numbers. So it is represented as a sequence of numbers in two ways. As we have seen that discrete time signal is the continuous signal whose samples are taken at some certain time intervals. So that continuous signal becomes a sequence of numbers. So how to represent that? One is it is represented in the sequence way. Second, it is represented in the graphical way. In the sequence, see here, suppose first sample is 2 at the reference 0. The second sample, that is the first, is 1.7, second is 1, third is 0.7. And the samples taking previous to that are represented in the negative, -1, -2, -3 and -4. -1 sample is 1.5, -2 sample is 0.7, -3 is 0.8, -0.8. In this way, we represent the sequence of numbers, that is the discrete sequence. Another way of representation is like this. So this arrow shows your 0th sample. Your 5 is your 0th sample, -2 is your first sample, 4 is your second sample, and so on. Similarly, previous to that, the samples taking previous to the 5, this 0 sample, are 1, that is -1 sample, 3, that is -2 sample, 1, that is your -3 sample. It is represented something like that. Your x0 is 5, your x1 is -2, your x2 is 4, similarly x3 is your 6. On the other side of that, x minus 1 is your 1, x minus 2 is your 3, x minus 3 is your 1. So this is the two ways of representation of the discrete sequences. One is the graphical, another is the sequence. We can use both of them. Now we come to some basic sequences. Basic discrete sequences used in the DSP. First is unit sample sequence. It's quite simple. It has a value of 1 for the 0th sample. All other samples are 0. Delta n is 0 when n is not equals to 0. Means when n is equals to 1, 2, 3, -1, -2, anything like that. Delta n is 1 when n is equal to 0. At n is equal to 0, it has a value of the 1. At n is equals to 1, 2, 3, at n is equals to -1, -2, 3, all these values are 0. This is called the unit sample sequence. Unit step sequence. In unit step sequence, we have all ones for the values of the n that are positive. For n is equal to 0, 1, 2, 3, 4, 5, 6. This sequence has a value of the 1. For any negative values of the n, it has 0 values. For -1, -2, -3, -4, all these are the 0 values. So unit step sequence un can be mathematically represented as un, it has a value of 1 for n is equal to 0, 1, 2, 3, 4. That is the positive values of the samples. For the negative values of the sample, it has the value of the 0. Similarly, third is unit ramp sequence. It has a value of the 1 at 1, it has a value of 2 at 2, it has a value of 3 at 3, it has a value of 4 at 4, 5 at 5 and so on. And 0, it is 0. Minus 1, it is 0. Minus 3, it is 0. So mathematically, it is represented as unit ramp sequence as Rn is equals to n. For n is equals to 0 and more. N is 0, this is 0. N is 1, this is 1. N is 2, this is 2. N is 3, this is 3. For any negative values, this is 0. This is known as the unit ramp sequence. So next is the exponential sequence. Xn is equals to A, capital A into A raised to power n. N is equal to 0, A raised to power 0. N is equals to 1, A raised to power 1. N is equals to minus 1, A raised to power minus 1. N is equals to minus 2, this is raised to power minus 2. So, in exponential sequence, we have the four types of the sequences depending upon the value of the A. If A is more, this is exponentially increases. Suppose A is 2, what you will have is 2, then 2 raised to power 2, 4, then 2 raised to power 3, 2 raised to power 4, that is exponentially increasing. If A has a value of between 0 and 1, that is like minus 0.2, 0.3, 0.1, then it will be exponentially decreasing. If it has a minus value, this A is less than minus 1, like minus 2, minus 3, minus 4. We will have an exponentially increasing sequences, but with alternate change in the sign. Minus 2, suppose we have minus 2. Minus 2 raised to power 1 is minus 2. Minus 2 raised to power 2 is 4. So it has changed its sign. So any odd values of the power makes it negative values, and any even values of the power make it the positive value. So these are the alternate in the sign. Similarly, if it is less than 0 to minus 1, like minus 0.2, minus 0.1, something like that, then it will be exponentially decreasing along with the alternate signs of the values. So in exponential sequence, we have the four types of sequences depending upon the value of the A. Now, next and very important sequence is sinusoidal sequence. See here, it is represented as xn is equals to A cos omega naught n plus phi. Omega naught is the frequency, phi is the phase for all the values of the n. If it is represented, it's something represented like that. Again, it will have the discrete values and it is sinusoidal in nature. It can also be represented as xn A e raised to power j omega n plus phi. That is equal to A cos of omega n plus phi plus j sine of omega n plus phi. Again, that is a sinusoidal signal, representation of the sinusoidal signal. And the shape of the sinusoidal signal is something like that, and that is oscillatory in nature, as we know. This becomes one time period, this becomes another time period, and so on. Now come to the frequency of the discrete sequences. The concept of the frequency is different in discrete sequences as compared to the continuous sequences, continuous signal. We will see how. Frequencies omega plus 2 pi r are indistinguishable. What does that mean? Suppose we have a frequency we have a discrete signal of frequency 2 pi. We will have another sequence of frequency 4 pi. Both will be the same sequences, indistinguishable. Suppose next we have 6 pi, 8 pi, something like that. All are indistinguishable. Suppose we have a sequence discrete signal having a frequency of pi. Another sequence is 3 pi. Both sequences will be the same. We will see why, or mathematically it is proven. Xn is e raised to power aj omega n. Suppose frequency this frequency is increased by a value of 2 pi. What will happen? It will become omega plus 2 pi. It becomes a e raised to power j omega n e raised to power j 2 pi. And e raised to power j 2 pi is equals to 1. So this sequence is a e raised to power j omega n. That is same as that. If frequency is increased by 2 pi, we will get the same sequence. As e raised to power j 2 pi is cos 2 pi n plus j sin 2 pi n. Sin 2 pi n is 0, cos 2 pi n is 1. So this becomes 1. And the sequence is same. So if you add omega plus 4 pi, again you will get the same sequence. So, but in case of continuous signals, the frequency can take any value. You keep on increasing the frequency, the oscillations increases. But in the case of discrete signal, this is not the case. Its frequency repeats itself after every 2 pi. It may be minus pi to pi. It may be 0 to 2 pi. It may be pi to 3 pi. But you can take the values of only 2 pi. After the 2 pi, it will repeat itself. So, in general, we can say the frequencies omega plus 2 pi r are indistinguishable. We can't distinguish between these two frequencies. That is the major difference between the discrete sequence and the continuous signal. Again, I am repeating, in the continuous signal, we can have any value of the frequencies. You keep on increases the frequency, the oscillations will keep on increases. But in the case of the discrete sequences, we can have only the frequencies in the range of 2 pi. 0, 2 pi, 4 pi, 6 pi, all will be the same. Similarly, pi, 3 pi, 5 pi, 7 pi, all are the same. Now, another major difference between the continuous signal and the discrete signal is their periodicity. How a discrete signal is periodic? If it repeats itself after some certain number of the samples. Xn, it is the same as xn plus n. Suppose n is equals to 5. It will repeat itself after every 5th sample. That is the periodic signal, where n is an integer. Now see here, xn is equals to a cos omega n plus phi. Suppose we take n plus capital N. It should be the same. So it becomes omega naught n plus omega naught capital N plus phi. Both should be the same. This means these two will be the same if omega n, this value, it is equals to 2 pi. Because cos 2 pi plus any angle is the cos of that angle. So omega n has to be equals to 2 pi k. So the depending upon the value of the omega, sinusoidal signal may or may not be periodic. That is the difference between, that is a very important difference between the continuous signal and the discrete signal. In continuous signal, we can have any value of omega. But in the case of the discrete signal, we cannot have. For some values of the omega, sinusoidal may be periodic. For some values of the omega, sinusoidal may not be periodic. We will take examples to make it more clear. Suppose now I am comparing two values. Omega is equals to 1 and omega is equals to 3 pi upon 4. As from the previous equation, n is equals to 2 pi k upon omega. Suppose omega is equals to 1. Capital N become 2 pi k. N is an integer. There is no value of the k for which n is an integer. So for a frequency omega is equals to 1, the sequence is not periodic. Now on the other hand, take omega is equals to 3 pi upon 4. You put the value of omega in that, what you get is k is equals to 3n upon 4 and n is equals to 4k upon 3. Suppose k is equals to 3, n is equals to 4. For the value of the k is equals to 3, your sequence is periodic with a time period of 4. Capital N is equals to 4. So it is very much clear from this example. For omega is equals to 1, the signal is not periodic. For omega is equals to 3 pi upon 4, the sequence is periodic. But in the case of the continuous signals, what we know is it can have any value of the frequency. There is no limitation on the value of the omega, on the value of the frequency, so as the signal to be periodic. There are the two very major differences between the discrete signal and the periodic signal. Continuous signal. In discrete signal, frequency can vary in the range of 2 pi only. After that, it repeats itself. But not in the case of the continuous signal. The second difference is, in discrete signals, we cannot have any value of the frequency for the signal to be periodic. But in continuous signals, you can have any value of the frequency for it to be periodic. Now, start with the continuous signal. Xt is equals to a cos omega t plus phi. This increases, oscillations increases. There is no limitation on the value of this. You increase the frequency, the oscillations will increase in the case of the continuous signal. But in the case of the discrete signal, you increase the frequency from 0 to pi, oscillations will increase. You keep on increasing the oscillations from 0 to 2 pi, the oscillations will decrease. It does not keep on increasing as compared to in the case of the continuous signals. So 0 to pi, oscillations increase, pi to 2 pi, the oscillations decrease. So it will have the maximum oscillations at pi and minimum at the 0 and the 2 pi. Similarly, the maximum oscillations can be at 3 pi, 5 pi, 7 pi. Minimum oscillations at 0, 2 pi, 4 pi, 6 pi and so on. So that is the difference between the concept of the low frequency and high frequency in case of the continuous signal and in the discrete signal. So next we will come to some basic sequences or operations that are performed on the discrete sequence. As I've told you, discrete sequences or in that case, any signal has two variables. One is the independent variable and another is the dependent variable. So the operations are of two types. One is on the independent variable, another is on the dependent variable. So first we will study the transformation of the independent variable, or you can say the operation on the independent variable, on the samples, number of the samples. Okay, not the value of the sample. Value of the sample is your dependent variable. The number of the sample is your independent variable. First we will start with the time shift. Time shift can be of two types. One is delay, another is the advance. Let's start with the delay. Suppose we have a sequence xn and its delayed signal is yn, that is equals to xn minus n naught. It is delayed by n naught samples. For example, yn is equals to xn minus 2. This means xn is delayed by 2, that makes the signal yn. You take a sequence, delay it by 2 samples, what you get is your delayed sample. Suppose we have xn. So the 0 sample has a value of 5, sample 1 has a value of minus 2, sample 2 has a value of 4, sample 3 has a value of 6. Similarly, minus 1 has a value of 1, minus 2 has a value of 3, minus 3 has a value of 1. Suppose this signal is delayed by 2. See, each and every sample in this sequence is delayed by 2. Fifth is coming at the 0 sample. Now it is coming at the, this is a 0, this is the second, delayed by 2. Minus 2 is the first sample. Now minus 2 is the third sample. Again it is delayed by the 2. 4 is your second sample. It is delayed by 2, and so on. Delay is similar to something like that. Your train is coming at 5 p.m. Now it is coming at the 7 p.m. It is delayed by 2. How to calculate that sequences is y0, put the n, the value of n is equal to 0, put the n value of n here is equal to 0. What you get is y0 as x minus 2. Similarly y1, similarly y minus 1 on the another way. Now the reverse of that is advance. Your train was coming at 7, now it comes at 5. This means it is advanced in time. If your sequence is coming at the third sample, now that is coming at the first sample, this is advanced by 2. That is xn plus 2. Here it is sample, this comes at the 0, now it is coming at the minus 2. It is advanced by 2. Similarly, we can have x0 as x0 plus 2, that is x2, y1 as x1 plus 2, that is x3, y minus 1, that is x minus, minus 1 plus 2, that is x1. So this is the two types of the time shift. One is the delay, one is the advance. In delay, your sequence will be delayed by any number of the samples. It may be 2, 3, 4, 5, anything like that. In the advance, your sequence will be advanced by some number of the samples. Now, next is the folding. Folding is taking the mirror image of the sequence around the 0th sample. You put all these samples on that side, you put all these samples on that side. Now minus 2 will become 1 and 1 will come over here. 4 will come at 3, 3 will come at 4. 6 will come at 1 and 1 will come at the 6. So this is known as the folding, x minus n. Next is folding and time shifting are not commutable. This means if you fold a signal and then time shift is not equal to you time shift and then fold it. See here, what you do is you first time delay it, then fold it. So you time delay xn signal by k samples, it become x n minus k. Now you fold it, your n becomes minus n and your sequence becomes x minus n minus k. This is a result of what? First time delaying the signal, then folding it. Now take the otherwise, fold it, then time delay it. Now in this is, first you will fold it, then you do the time delay of that. You fold it, your n becomes minus n. You time delay it by k, n becomes n minus k, and this sequence becomes x n plus k. These two are not the same. This means time delaying a signal then folding it is not equal to the signal that is first folded then time delayed. So these two are not equal. Time scaling. There are two types of the time scaling. One is the down sampling, one is the up sampling. Yn x is equals to 2n. What happens in that? Sampling period doubled and sampling frequency half. In a certain time period, if we are taking the 10 samples, now it will become 5 because the sampling period is doubles. You left every alternate sample. You have the 10 samples. Now what you will do is, you take the first sample, then the third sample, then the fifth sample, then the 7 samples and so on. So in the case of the down sampling, your frequency will be halved and your sampling period will be doubled. Sampling period doubled means we are taking the samples at more time period. Suppose first we are taking the samples at every 1 millisecond. 1 millisecond, 2 milliseconds, 3 milliseconds. Your sampling period is 1 millisecond. Suppose sampling period is doubled. Now what will you take is at 1 milliseconds, then the 3 milliseconds, then at the 5 milliseconds. So obviously frequency will be half. And in the case of the upsampling, now your sampling period half and the frequency is doubled. Suppose in a certain time period, we are taking the 10 samples. Now in that time period, what we will take is 20 samples. Suppose we have a sampling period of the 2 milliseconds. We take the samples at 2 milliseconds, then 4 milliseconds, then 6 milliseconds, then 8 milliseconds. When it is upsampling is done, sampling period is half means now we will take the sample as 1 at 1 millisecond, 2 milliseconds, 3 milliseconds. So number of the samples will be doubled. Frequency sampling will be doubled. That is the time scaling. So all these are operations: delay, advance, time scaling, folding. All these are the operations done on what? Independent variable. That is the number of the samples. Next what we will do is the operations on the dependent variable. Operation on the amplitude. Next is the manipulation of the dependent variable. It's quite easy. Any addition, multiplication, division between two sequences is done on the corresponding samples. Suppose you are adding two sequences. Zeroth sample of one sequence will be added to the zeroth sample of the other sequence. First sample of the one sequence will be added to the first sample of the another sequence. Similarly, suppose you multiply two sequences. Zero sample will be multiplied by the zero sample. First sample will be multiplied by the first sample. Second sample will be multiplied by the second sample, and so on. Similarly, we can do the division. One more type of the operation is the scaling. That is the multiplication of each sample by a constant. Suppose we multiply a sequence by 2. All samples will be doubled. The value which has the sample which has a value of 1, it becomes 2. The sample which has a value of 2 becomes 4. The sample which has a value of 4 becomes 8. That is the manipulation of the dependent variable. So in operations, we will have two types of the operations. One on the independent variable, that is time shifting, folding, and sampling, downsampling and upsampling. In manipulation of the dependent variable, in the operations of the dependent variables, it is quite simple. Whatsoever the operation you have to do it on the corresponding samples. If you have to add 2, add 0th sample to the 0th sample, first sample to the first sample, you have to multiply first with the first, 2 with the 2, 3 with the 3. Scaling is the multiplication of each sample by constant value. That is the manipulation of the dependent variable. Thank you.